Okay, so it's with great pleasure that I'm introducing Steve Furber, Professor of Computer Engineering in the Department of Computer Science at the University of Manchester. After completing a BA in Mathematics and a PhD in Aerodynamics at the University of Cambridge, he spent the 1980s at Acorn Computers, where he was a principal designer of the BBC microcomputer and the ARM 32-bit RISC microprocessor. Over 200 billion ARM-powered chips have since been manufactured, powering much of the world's mobile and embedded computing. He moved to the ICL chair at Manchester in 1990, where he leads research into asynchronous and low-power systems, and more recently, neural systems engineering, where the Spinnaker project has delivered a computer incorporating 1 million ARM processors optimized for brain modeling applications. So help me welcome Steve Furber. Thank you very much.
Well, thank you very much for that introduction. It's great to be here. I've spent the weekend in Amsterdam enjoying the beautiful weather and sights of the canals with my wife. So it's wonderful to be here. I have spoken at a tinyML event, I think, last year online. This is my first opportunity to meet you in person. So that's a privilege. Now, most of my work in Manchester is focused on the Spinnaker project, which is not particularly tiny. In fact, you've heard it's a machine incorporating 1 million ARM processors. You'll see a picture of it later in the slide deck. But today I'm going to talk a little bit about that, but mainly I'm going to talk about a novel mechanism for edge machine learning, which has emerged from the research in the group, and for which there's a poster and there's a demo next door. And Michael and Jakob, who are sat over at the front on this side, they will be here throughout the conference if you've got questions about this particular piece of technology. So why have we been worrying about this? And we start with, what are the issues with AI? Now, I'm perfectly aware that for this audience, most of this is familiar stuff. You'll know what's wrong with AI. That's why you're interested in tinyML, right? Because standard AI is too big. But we all know that the AI has made great strides over the last 20 years. It's doing very impressive things. But there are problems that the large AI systems that we hear about in the news require formidable amounts of energy, particularly in the training phase. People compare the amount of energy required to train the latest large language models with, the number of family cars throughout their entire lifetime. I'm never quite sure how they do those comparisons. But these are huge amounts of energy. And it's already becoming very expensive and the domain only of the largest companies that can afford to develop these large models. We can't allow the energy requirements of these systems to continue growing super exponentially, and there'll be all sorts of silly consequences if we follow the current trends in increasing scale and performance. And even at the lower end, if we're trying to apply this technology in systems such as autonomous electric vehicles, there's concern over the amount of power that's required to run the AI that's required in these vehicles. And we'd like to bring the 100 watts down to 1 watt. I was talking earlier to Alessandro, what is tinyML? And apparently you started with the idea that really it was milliwatts. Now, I don't think the automotive people need to get down to milliwatts. I think they'd love to. But getting down to watts would be a significant step forward for the kinds of things that they're trying to do. And, of course, legislation is going to come in that's going to impose increasing numbers of constraints on what can be done. And the numbers for large-scale models are just getting to the point where this is infeasible going forward. But that's not the only problem. Energy is a big problem, but it's not the only problem. The systems that are built using conventional mainstream AI suffer from being rather brittle, and they're rather easy to fool, and they're rather hard to explain. So when they produce an inference or a recommendation, it's quite hard for them to justify how they come to that conclusion. So this is partly a result of the fact that they use huge parameter sets. I believe there's over 100 trillion parameters for GPT-4. And with that number of parameters, it's almost inevitable that you're going to overfit the data, okay? And some of the problems of these large systems are a result of that overfitting. And they're very easily fooled. So you can make small changes to an image, and the system makes complete errors that humans would not make. And they can make these errors with very high confidence. So, for example, if you look at these pictures at the bottom here, the picture on the left is a panda. The network classifies this with 57.7% confidence. It's not that high, but it's reasonable. And then you add a relatively small amount of noise, which apparently the network thinks is a nematode, although I can't actually see any nematode in there. It looks like noise to me. And if you add that very small amount of noise to that panda, then the network suddenly becomes very confident it's not a panda, but it's now a gibbon, okay? Now, I don't think anybody here in the audience would make the mistake of deciding that that noise has turned the panda into a gibbon. But this is a characteristic of these large networks and their brittle nature. So where do these changes come from? Well, often they're from random errors, so sort of innocent sources, but increasingly as AI gets deployed in real applications, they'll become the target for malicious attacks. And if they're so easy to fool with random errors, then where will we end up with when malicious attacks start to arise and people deliberately start trying to break these things? And obviously, if they're trying to break them and the AI system that you're talking about is responsible for controlling the autonomous vehicle which you're traveling down the highway in, this is a serious problem, okay? And so what we really want are systems that are much more robust to noise than the current large AI systems. And furthermore, the topic I mentioned earlier, explainability, is important. We need networks where it's possible to say, okay, you think that's a gibbon, why do you think it's a gibbon? You know, what's your justification? It's not enough just to know that you're 99% sure it's a gibbon, particularly when we know that you're wrong. We'd like to know why you think it's a gibbon and why you are confused by what's obviously a panda, and you knew it was a panda before we added a bit of noise. You know, why has it suddenly become a gibbon? So explainability is a growing area of interest in the business. The other problem with big networks, of course, is that they're fairly static. The training is so expensive that once they're trained, they're kind of frozen. Whereas most real-world systems, you really want to be adaptable. So we have the training set, the huge cost, the learning is frozen. What we'd really like is systems that are better matched to the real world, where everything is constantly changing, and we want the system to be adapting to those changes and making a more sensible interpretation of the information that's then available. And so there's a growing number of research projects that are trying to address this issue of building systems that can learn online, that can learn from single examples, that can work better and adapt better to the real world as things change. Now, where we come from in the neuromorphic community, of course, we start from a slightly different place from mainstream AI. And what we're interested in is trying to understand how it is that biological systems manage to solve these kind of problems much more effectively than our engineered systems. And they do things differently. Even very small biological systems, such as the example here, an insect brain, which is only the order of 100,000 neurons or maybe slightly more, they are very effective at adapting in the real world, doing very sophisticated control. We yet to build an aeroplane that can land upside down on the ceiling, which a fly can do. The problem is we'd like to apply those principles, but of course at the moment we don't understand them, right? So we can't build a fly brain to control a drone because we still don't fundamentally understand how a fly brain works. But understanding is advancing in that space. What can we say about biological systems? Well, they learn continuously. You don't stop learning when you're born. In fact, you've barely started. You learn throughout your life, you adapt. Even when you get to my age, learning is just about possible. It gets harder, but we can still do some. And these biological brains use tiny amounts of energy. So they're highly relevant to this community. The human brain is very much at the large end, runs on about 20 watts. Insect brains are tiny fractions of that. How do they do it? We don't really know. The other feature that we'd really like to track addresses this issue of being easily fooled. Now, you can fool biological brains. We have optical illusions that fool our brains. But on the whole, we're much more robust. And we can work in a noisy environment, and we can operate effectively and safely. And what we have is a system that has this characteristic of graceful degradation. So when things get difficult, our performance goes down, but it doesn't suddenly fall off a cliff. And again, that's really what we'd like to see in our engineered systems. So with these factors being brought into account, we've tried to learn from biology, and we've created this bit brain concept, which you may, I'm going to explain it, and the idea principally comes out of Michael's mind over there. But he's been putting things together as we've been studying biology and the different factors and the things that we seem to be missing in current AI systems. These have kind of come together to form a very interesting synthesis of concepts. So what's it all about? Let's have a look at the key features. The summary of BitBrain is that it's an innovative working mechanism, which is the sparse binary coincidence memory, with an infrastructure around it, which we call BitBrain, although whether we can stick with that name is a bit of an issue because there is a Spanish company that uses the same name, so we may have to do something about that. And what this is it's a novel synthesis of ideas from sparse coding, computational neuroscience, and information theory. Okay, so these are the fundamental concepts that are coming together. And we have filed a patent on this concept. And what this delivers for us is single-pass supervised learning. So this is a system that can learn from a single example. And I'll show a demo of that shortly. So the computational cost of training is extremely low compared with mainstream AI systems that use error backpropagation that requires hundreds of epochs of training before it converges on a sensible behavior. These systems deliver accurate inference, and as I hope to show you, it's very robust against imperfect inputs. Okay, so it addresses this issue of brittleness or criticality. And because of the single-pass nature, the mechanism is capable of learning continuously and adaptively and running online and improving over time. And of course, to address the concerns of this audience. It uses small amounts of energy, it's fast, and it can be supported, as I'll show, on both conventional hardware and on neuromorphic platforms. So it's reasonably well suited to the interests of this community, I think. And the particular instances we'll show, I mean, we've implemented this on a standard laptop, of course, but also I'll show it running on Raspberry Pi and also on Spinnaker, which is our neuromorphic platform at Manchester. So that's what BitBrain is about. Now here's the technical bit. How does it work? Well, we start with the concept of an address decoder element. And this looks like a fairly simple standard neuronal feature detector, but it's very much based on what we've come to understand about the biology of dendritic computation. So biological neurons are not the kind of neurons you see in standard AI. They don't simply do a weighted sum of their inputs and then pass them through a nonlinear function to generate an output, okay? The biological neuron is much richer than that as a computational device. And I don't think we fully understand even the individual neuron yet, but what we do know is that there are local computations going on branches of the dendrites, okay? So the dendrites are the sort of hairy tree-like structures that collect inputs from other neurons and feed them in. But within those dendrites, there are nonlinear processes going on, so that local areas of the dendritic branches are doing some local recognition. And when that local recognition gets sufficiently exercised, that stimulation then propagates further through the system. So we take that idea of using small, localized dendritic recognition mechanisms, and each of those looks at a small sample of the input data, works very much like how you understand the neuron to do. And then we put these together into a recognition system. So, what does this mean in practice? Well, the simple example here, and some of the examples I'm going to show you are based on standard MNIST data set. So I guess everybody's familiar with this. MNIST is a monochrome handwritten character benchmark where each character is normalized and rotated within a 28 by 28 grid. It's grayscale coded. And within BitBrain, each of these address decoder elements samples a small number of pixels from this input space. Now, in the image shown here, these pixels seem to be selected at random. In general, we cluster them a bit so that they sample from a localized area of the image. This isn't a requirement for all uses, but for this particular one, this appears to work quite well. And we take these samples and feed those into one address decoder element. And then we have lots of address decoder elements, all taking different samples from the input image in some fairly random but spatially localized way. And of course, what I'm showing you here is the image input, because that's one that's familiar to most people, and it's relatively easy to see what's going on. But in fact, the input can be any kind of input stream that can be represented with binary information, and we can sample from it in the same way. And when we do that, the ADE operates a bit like a neuron in that it fires when the sum of the connected input values multiplied by their respective weights reaches the threshold. Okay, so that's a fairly standard model. Now, that threshold in the BitBrain system is adaptive homeostatically. So what we do when we set up the system is we set those thresholds so that all the ADEs fire at roughly the same rate, roughly 1% of the input samples, something like that. Now, what do we do with those ADEs? Well, we have lots of them. So we can think of the memory, the sparse binary coincidence memory, as an array with an address decoder down each side, where each address decoder is a long line of these address decoder elements. Okay? So again, the examples I show you are two-dimensional. You can make them in higher dimensions. We've played with three-dimensional SBCs. There doesn't seem to be sufficient advantage to merit the increase in cost because, of course, the memory requirement goes up as the power of the dimensionality. And typically, we're talking about address decoders, each with 1,000, 2,000 ADEs in, that kind of scale, so that you have a matrix which is 1,000 by 1,000, something like that. And when we feed an input, so the image at the top is fed into both of these address decoders. Each of those may have elements with different numbers of samples. So the one at the top may be taking 6 samples per ADE, the one at the left may be taking 10. These are parameters that can be played with. And when those address decoder elements fire, as I say, roughly at 1%, so if it's 1,024 ADEs along the top, then 1% of 1,024 is about 10, I think, yes. Doing mental arithmetic while standing up here is quite difficult. So you get 10 firing along the top and 10 firing down the side. And where those 2 firings coincide within that matrix, within the million elements in that matrix, you get the order of 100 active locations. Okay? And so this is the binary coincidence. What effectively each ADE is doing is it's a feature detector, and what each of those active locations is marking is a coincidence of 2 features. So one feature in the top address decoder, one feature in the left-hand address decoder. And the thing to note here is that that activation pattern is sparse because only a small percentage of the ADEs are active at any one time. And so you get a relatively small number of active locations. And each coincidence of active ADEs activates a memory location that can be used to read or write information about the class which has activated it. So it's that pattern of coincidences which is the marker of the particular class. So let's look at a particular column there corresponding to one of the ADEs along the top and the set of ADEs down the left. And if we look at that column, then at each of those locations we have a number of bits of memory. And the depth of the SBC is the number of bits of memory you have at each of those coincidence locations. In the simplest form, where we use one-hot encoding for the classes, in the case of MNIST, where there are 10 classes, we'd have 10 bits, okay? You can use other encodings, but again, the one-hot mechanism is the simplest to understand. And then if we look at what's in those memory locations, we have a number of bits that have been set by previous operations, but the current class that we're writing in will then set the blue bits. So here we're writing in an example of class 6, and so in those locations we set the 6th bit in the one-hot encoding. And that's how we store the information about the class that we've seen in the training set. And okay. Yeah, so we set those 3 bits, and that's stored information that these coincidences have been found in an example of that particular class. So writing to the SBC, you go to all the active memory locations and you set the bits. It's a simple operation. No point in doing it twice, because the second time we'll do exactly the same as the first, add no further information. And then if we read from it, what we do is we count the number of set bits in all the active locations, and the class that has the highest bit count is the inferred class of that device. So basically what we're saying is, with this test example, how many of these coincidences match each of the different classes that we've used in training, and the one that has the highest number of matches defines the class of the test example. Okay? So it's very simple, it's binary, there's no complicated arithmetic involved, and as I've said, the example I'm showing you assumes one-hot encoding, but there are other ways that this could be implemented. So what does it give us? Okay, does it work? It's very simple. And the answer is, yeah. Oh. So here's an example, again, using MNIST. And these are the basic results from MNIST. MNIST is quite a nice data set. It's balanced, which helps. There are 10 classes. And what you see here, and these colored curves, just to understand this, is that each of the colors corresponds to a different amount of training noise. Okay, so the yellow, which is highest at the left, that's an SBC or a bit brain that's been trained with no noise. If you add noise in training, which just means varying the, adding statistical noise to each of the pixels that are sampled to generate the training activations. Then as you add noise, you see that with noise-free test examples, the results get a bit worse. But if the data you're testing against itself is noisy, and that's the horizontal axis along the bottom, then what you see is that at significant noise levels in the test example, then if you trained with noise, you get a much better inference when you test with noise. And so this is sort of exploring the space of the system's immunity to noise in the input. If you're using this in a noisy environment, you want the best performance that you can. So what could we compare this with? Well, we can look at that as a three-dimensional picture, which may or may not give you more information than the graphs. I find these harder to read than the individual graph curves, but 3D graphs look pretty, so we've got to have one. And let's compare it with something. So one of the networks that's quite old and being used with MNIST quite a long time is LeNet5. It's quite a respectable network. This takes, unlike BitBrain, which is trained in a single pass over the training set of MNIST, this is trained over 100 epochs, so it's incrementally working towards its optimum performance. And again, we're using the same noise technique, so we're adding noise both to the training set to give the different colored curves. And what you see here is, again, the yellow curve is trained with no noise and has the highest performance with zero noise test data, but that performance drops off very quickly as we add noise to the test data. And if we train with a bit more noise, the performance doesn't drop off as rapidly. Now, it's all very well looking at that. How does that compare? Well, we have to make the y-axis the same to actually see what's going on, okay? And this gives you a fairly clear indication. The BitBrain performance at the top in this graph shows you that the drop-off with noisy input data is very small compared with LeNet5. Again, you have to scale these things right to see a sensible comparison. So BitBrain's noise immunity appears to be very good here. Now, LeNet5 is not a state-of-the-art network for tasks such as MNIST. And if we look at a much more complex, more modern network for doing MNIST work, that would be CapsNet. And even here, with this more sophisticated network, we can see that BitBrain is performing well under noise. Now, its peak performance is not as good, okay? It's quite hard to see with these graphs because we've scaled them to the same size so that we can see the overall trend. But if you look at the CapsNet performance under low noise conditions is very close to 100%, and the BitBrain performance is around 95%. So we're not claiming it's the best classification system under all conditions, but under noisy conditions, you can see it's performing pretty well compared with what is really quite a sophisticated network for this problem. And now MNIST is often viewed as a rather trivial test. A slightly tougher challenge is EMNIST, where the number of classes is now 62. The setup is exactly the same here as for MNIST. It's a much harder problem. It's unbalanced, so there aren't the same number of training examples of each class, and there's obvious class aliasing, which makes this hard. So the examples here are little o, big O, 0, okay? We all have trouble with those, and there are several other examples. And the BitBrain performance is shown on the right here, and again we can compare this with LeNet 5, and we can see that the BitBrain performance is much more stable under noise than LeNet 5. LeNet 5 tends to work reasonably well up to the degree of noise it was trained with. Okay, so if you look at the red curve, which is trained with 10% noise, when the test noise is 10%, or in fact it's up to 20%. No, sorry, the red curve is trained with 20% noise, and when you test it with 20% noise, it's doing quite well, but you test it with 40% noise, and the performance has collapsed. The BitBrain behavior is much smoother, and it's much more noise robust. And again, you can do the same comparison with CapsNet, and you see a similar thing. The peak performance at low noise is not as good, but the performance under higher noise is much smoother, and the degradation is much more gentle. Now, that's doing direct comparison on classification accuracy. Of course, what I've emphasized is that the BitBrain training is single pass, so it sees each example once. If you show it each example twice, it makes no difference at all because the bit set is deterministic. It'll be the same bits. Now, of course, if you train it with noise, then that's not quite true because you can have different noise for each training set. But basically, we're using single-pass training. And so it's valid to compare it with other single-pass methods, and a number of these have been published. They have names which we don't fully recognize. But the green bar at the left is BitBrain classification accuracy, and the red bars are CNNs trained for only one epoch, so they are reasonably state-of-the-art networks. Of course, they're not intended to work with single-pass training, but that's how well they do perform if you use single-pass training. And the blue bars are systems that are designed specifically to work with single-pass classification methods. And what you see here is that BitBrain slightly outperforms the best of those. So in the context of single-pass training, it performs pretty well. And if you like reading numbers, then there's another comparison in this table where here it's doing two class comparisons, 0 versus 1 and 8 versus 9, comparing it with a number of the standard methods, SVM methods. And what you can see is that the BitBrain performance on these particular tests is higher than any of the others. Okay, so how does this work in practice? Well, you can see this in the demo room. The kit's here. It's all nice and portable. But here's an example of Raspberry Pi. This is Jakob's finger, I think, starring in this video. And sorry? Now, the histogram on the right is showing the counts for each of the digits, and if you look very carefully, it stopped, okay? But what you saw there was with what's going on? Am I doing anything? No, you're doing something. Okay. In this particular case, we're training a new symbol. So this is a network. This is a network that was trained on MNIST. Maybe you had better go and watch the demos next door. This is a network that's trained on MNIST, which has 10 classes, but the system's set up to store 16 classes, and a new class is used to store this right arrow character. And having been shown a single example, it's then inferring a similar right arrow, and you can see the new class to the right with the red bar is confidently showing that it's recognized it. And in this case, it's just seen one example of this class, and it's already doing quite a good job of recognizing it. Now, the test setup here, which again you can see next door, it's a standard Raspberry Pi with touchscreen. Okay, so these are cheap things you can buy from Amazon for almost nothing. And this is actually running the BitBrain algorithm on the Raspberry Pi itself. So it's running it. This is a software model. At the bottom of the picture here, there's a small Spinnaker board which will come into play in a subsequent video, which you may or may not be able to see when we get there. So I don't know, how many people in this room are already familiar with Spinnaker? Okay, not so many. Right. Well, Spinnaker has been the main focus of my research group in Manchester for the last 20 years. At the start of this project, we set ourselves the goal of seeing if we could put 1 million ARM processors into a single computer system to run models of biological brains in biological real time. Okay, that was the goal. From the outset, it was clear that even with 1 million ARM processors, you don't get close to the scale of the human brain. That's clear for starters. At that time, we thought we'd get to about 1% of the human brain, or maybe, as I prefer to think of it, 10 whole mouse brains. The mouse brain is conveniently very similar to the human brain, but 1,000 times smaller. That's how the numbers work out. Now, with what we know now, even those numbers look optimistic. But I still reckon we could probably do a whole mouse brain on this machine if somebody could find the network for us. Of course, one of the problems is we don't have the full data set for the mouse brain. But in principle, that's what we could do. And we've been building this machine for a very long time. So we started off designing a microchip ourselves. That was between about 2005 and 10. We packaged the chip with a standard memory chip inside an industry standard package. And you can see what's inside the package there. The darker rectangle on top is the memory chip. The lighter, squarer chip underneath is the compute layer, which is the chip that the group designed. And that incorporates 18 ARM 968 processors. Okay, so they're standard ARM processors with local memory. We can assemble those packages onto arbitrary 2D surfaces, and we use this printed circuit board, which has 48 of these packages on. 48 times 18 is 864 ARM cores on the board. And then we can use that board to assemble larger machines. And in November 2018, we had a grand ceremony turning on the 1 million core machine, where we reached our original objective. And we did the usual dangerous thing in front of a live audience, of allowing the machine to boot and tell us how many processors were running. And I think we got to 1,010,000 or so. So we just, it did the right job. It got past 1 million, counting the cores up. At that scale, of course, it's highly fault tolerant, and therefore there are all sorts of dynamic tests to work out what's working, what isn't working, and telling the software how to configure the machine around the problems and all that kind of stuff. In fact, we'd had a 500,000 core machine running since April 2016, and those machines are offering an openly available service under the auspices of the Human Brain Project. But I realized that 10 standard data center rack cabinets full of processors is not what you call tiny. So it doesn't really qualify here. But what we've done, and Jakob has done this work, is map the BitBrain algorithm onto Spinnaker, largely treating it as just a massively parallel computing machine, but using its event-based communication system to send the information around. So if we look at that sparse binary coincidence memory, it has the 2 address decoders and all the coincidence cells. And what we do is we allocate one of the processor cores to a subset of the SBC memory, and we allocate one of the processor cores to a subset of the address decoder elements in each address decoder. And that way we can map the problem into a very parallel implementation across many cores on the machine. And when we do that, it can be done in various different ways. It's highly parameterized. But for example, we can end up with 32 cores supporting the address decoder elements and 384 cores representing the coincidence memory itself. And then this runs on the machine. And when we've done that, we can then show you it running with a bit of luck. So now the Spinnaker board at the bottom here, which is not 1 million cores, that's a 4-node machine, so that has 72 cores on that board. And that's running the SBC memory. And basically, you can't really tell the difference. The user interface that you can see next door, you can tell it to predict using the Raspberry Pi software version or using the Spinnaker version. And the two work indistinguishably. So how do you know it's doing what it says it's doing? That's ask Jakob. That's to prove that this is actually doing what it wants. So how are we doing? All right, getting towards the end of my slot. What can we conclude from this? Well, the status of BitBrain at the moment is that we've got this novel single-pass learning algorithm. It does reasonably accurate inference. Again, it's not the best in class compared with conventional ANNs that are trained over multiple passes. But it does seem to be the best in the single pass class. It's very robust to noisy inputs, as we've shown. It's simple and energy efficient, okay? There's no floating point. There's no back propagation. It's just simple binary operations. It'll support continuous and single shot learning. We showed the example of learning the right arrow, but of course there's a lot more than that you can do. And in terms of computational complexity, yes, it has a fairly big memory footprint because the SBC memory occupies a lot of bits. And there are various ways you can implement that, but if you implement it in the simple direct way, each of those bits represents a bit in memory somewhere. And if we implement that in a single-threaded mode on my Apple M1 MacBook Air, then its performance, it'll run through the MNIST 10K inferences in about half a second. So it's reasonably fast. I mean, that's comparable with the GPU implementations of the artificial networks. So it's pretty quick. And we've shown implementations on Raspberry Pi and Spinnaker. We've looked at a number of ways to improve this, although it's relatively early days in investigating all the possibilities. So if we use data augmentation in the form of jitter, which means we simply present each training example in 9 different positions centered around its normal position, so we just move it left, right, up, and down a bit. That gives you about plus 1% improvement in inference. And if you take on board the fact that when you've not got a balanced training set, you get different numbers of bits in each of the classes, and you do some normalization for that, that's worth about 1% as well. But these are all sort of things that we're playing with and still exploring. And there's a lot to do if anybody's interested in playing with this. We welcome contributions. We'd like, obviously, to go to more benchmarks. And we have done some work on some medical benchmarks, EEG and EMG benchmarks. I think I got the acronyms right. And again, I think that's something that can be demonstrated or at least talked about next door. And there again, with very little thought about the pre-processing, just sort of simplistic mapping onto the bit brain, it does seem to deliver state-of-the-art performance. And those are interesting examples because, of course, those are examples where the data is characteristically very noisy. Okay, so the system performs very well on that noisy data. But there are many more benchmarks we'd love to try. We like to look at more sophisticated pre-processing, for example, using a convolutional net on the front end. We're trying to work out how to layer this thing so that we can use these in series as well as in parallel. We're not sure how to do that yet. And there's different sorts of data we'd like to look at. We've not really done anything with the delays that are available, particularly on the Spinnaker implementation, that can be used for time series processing. And of course, we'd love some advances in the underpinning theory. There seem to be strong relationships between what we're doing with BitBrain and with kernel methods, which are a fairly well-researched area, but we haven't pulled that together yet. There's a paper on this which is now out in that's just a smile. Those were my instructions. If I see the camera flashing, stop talking and smile. Did I do that right? Yeah, so the paper that was out in Frontiers talks about the kernel methods and says a bit about that. So with that, I'll finish, apart from just mentioning that I've talked about Spinnaker. The second generation Spinnaker machine is now coming together. It's being developed in collaboration between my group in Manchester and TU Dresden, who are represented here. Where are you? Hector's, yes, at the back there, waving his hand. If anybody's looking for a job, they're recruiting. So that's as much of a push as I'll give you, right? So thank you very much, and I'm happy to take questions.